Now, to compare these a little bit more on equal playing fields, we can create a little graph here. On the left, you have the trusted relay key distribution networks, and on the right, we have entanglement-based key distribution networks. And the first row here is to say, are these available? So if you wanted to, you could go ahead and build a trusted relay key distribution network using off-the-shelf components. However, entanglement-based key distribution networks not so straightforward to implement. The quantum repeaters are actively being developed, which means you would kind of need an experimental setup to start building one of these entanglement-based key distribution networks. So you could begin working on it, but it wouldn't be ready for commercial purposes immediately. The second row addresses security risk as the network scales. On the trusted relay distribution, you actually need to have all these intermediate relays have access to the secret key, meaning that this actually does not scale as the security risk gets worse as the network scales because there's more points of the network that have the secret key. On the other hand, entanglement-based key distribution networks don't share a secret key with intermediate nodes, meaning that the insider threat risk is managed and the security of BBM92 or BB84 is just as strong in the bipartite case as it is in the network case. In the third row, we have the limitations on key rate. So in both cases, there's pretty severe limitations on the rate at which keys can be produced. On the left, it's how quickly can you actually send your qubits through a fiber to a receiving node, and what is your rate of qubit preparations, and how many of those qubits actually make it to their measurement at the other side of the optical fiber. And in the entanglement case, the key rate is limited by the end-to-end entanglement generation rates. So the higher the fidelity of your repeaters and the higher the rate of your entanglement sources means that you can create rate entanglement faster. However, if Alice and Bob are very far apart, there will be a lot of loss due to errors at quantum repeaters and/or entanglement sources not producing entanglement fast enough. Now, finally, we can talk about how flexible is a network. Is it multi-purpose or not? And trusted relay key distribution networks are really limited to prepare and measure protocols between neighboring nodes. So QKD works well for this. You can maybe apply these networks for randomness generation as well. However, there's very few applications beyond QKD or randomness generation that could be applied in these networks. On the other hand, entanglement-based key distribution networks are just use entanglement-based networking to distribute entanglement between any two nodes in the network. This is very, very flexible and generic, as any two nodes in the network could become entangled and establish a direct link with each other, and it allows many protocols to be implemented, ranging from quantum computing to sensing to security, many applications. So overall, entanglement-based key distribution networks will have advantages over trusted relay key distribution networks. They will both have more purposes and they're more secure. However, their only drawback is that they can't be implemented and deployed using off-the-shelf components like a trusted relay network can.